I will concentrate on how can we solve the Laplace transform problems by computers and Matlab. So these are the strategies or the procedures to solve Laplace transform problems. First, you have to define symbolic variables such as t or s, depending on what kind of Laplace transform we are going to take. The direct Laplace transform or the inverse Laplace transform. You have to declare t or s as symbolic variables. And then you can express the original function, the function you want to transform. And then you can call Laplace function. The function can be called in two ways. One is by default way, which maps the function of t into a function of s. And the other one is by this way you can introduce the original domain v, which is corresponding to the t, and the final domain vu, which corresponds to which the variable can be used for s, alternative variable for s. Let's see an example. And then you can cooperate your lattice function to get a better display of the results. And if you are trying to perform inverse Laplace transform, then you can call another function called I Laplace, which means for inverse Laplace. You can call this function also in two ways. Okay, so let's demonstrate this part by examples. Suppose you have a time-domain function like this. Suppose you have a time-domain function. So what is the Laplace transform? How can we map the original t-domain function into an n-domain? For this problem, we can see that t is a symbolic variable, so we can use a command like this to declare it. And then we can use this command to express the original function. And then we can simply use Laplace function to find the Laplace transform of the original function. So we can use these three steps to find the Laplace transform of our original function. First, declare symbolic variables, then specify the original function, then call Laplace function. And this will be the final result. So we say that this is the Laplace transform of the original function, time-domain function. And we can display it better if we call the pretty function. And this is the result. So if you have been given ft, you can easily code the Laplace function to get the Laplace transform of it. And it should be noted, I think some of you are quite interested in fractional order, fractional order things. This function may not work for some of the quite limited function. A fractional order function can be calculated by Laplace. For integral order calculus, it will work well. And in the second example, we just demonstrate the use of different variables. For instance, in the original function and in the x-domain function. So we have to declare x as a symbolic variable, and we want to transform it into a domain of W. Then we can use specify x and W. We should have similar results. So here is another example. Suppose we have a Laplace form of transfer function, we can call it. We will have some original control. Suppose we have a transfer function which is the Laplace form of a given function. Then what is the inverse Laplace transform of it? To solve this problem, we have first to declare the symbolic variables x for S domain, symbolic variables x, and time domain t. And then we can express the function g of s by commands like this. And then we can call the I Laplace function to find the inverse Laplace transform of a given function. And as a result, we get some very complicated results. And it can be seen that this result is quite unfamiliar with you, I think. Well, this is a coefficient. And the other ones are quite difficult to understand. This involves an algebraic equation. And says that you have to take the root of the algebraic equation. And then we can have different parameters and roots. I will explain this one to you through a simple example. Suppose you have s plus 1 s plus 2. The inverse Laplace transform will be something like this. And the original transfer function could be something like there is a numerator. In other words, if we have an original function, we first need to express it by partial fraction expansion techniques. However, if this one is very difficult to solve, if this one is quite difficult to solve, just something like this, if we cannot solve it easily, then it is very hard to get this kind of formulation. So the final result is heavily related to the denominator polynomial equation. If there are simple solutions, then the inverse Laplace transform will be very simple. Otherwise, it could be very complicated, completely depends upon the solution of this polynomial equation. So the solution we obtained so far are quite difficult to read. So now what we need to do is to call a VPA function. We discussed the VPA function before. Suppose we have 6 digits. The VP, this one is 6 digits, but this one seems to be still very long. And this should be something about the final transformation result. It should be combinations of E alpha t's and E alpha t sine beta t, E alpha t cosine beta t. Should be something like this. It completely depends upon the roots, type of roots in the denominator of the original function. So if you are trying to find the inverse Laplace transform and the root of the polynomial of denominator is not readily given, then you may get something like this. And if you are using VPA functions, you can get easy to read